This video is for biology for health science majors. We're now in Unit 2. We're covering the chemical basis of life. In this unit, we'll talk about elements and atoms and what they are. We'll talk about chemical bonds, so how atoms join together to create molecules. And we'll talk a lot about water's life-giving properties, and that's really going to be about water chemistry. So in this video, I'll be focusing on introducing atoms and elements to you. So we could break down all the stuff in the universe into two categories. We have energy and we have matter. So matter is all like the stuff that you can touch, the physical material aspect of the universe. And energy is sort of like power, the potential to make things happen. Without energy, matter would be unmoving. It would be stationary. It would be frozen in place. Nothing would be moving in the universe. Nothing would happen. Nothing would change. So energy is what animates the universe. It creates change. It creates movement. Creates an evolution of forms. So we have entire lectures devoted to energy later in the term. So this lecture is about matter. So matter is anything that occupies space and has mass. So this is the physical universe. Chemicals are the raw materials that make up matter. Now, matter is composed of chemical elements, and an element is a substance that cannot be broken down to other substances by ordinary chemical means. There are 92 elements in nature. And you may have seen a periodic table before. This table is not just a list of elements and their abbreviations. It also gives you important information about each element. We're going to talk about how to interpret periodic tables throughout this lecture. You'll notice, though, that there's more than 96 elements on here. There's 103. We've created new elements that are not found in nature in laboratories. And so each element is made up of a unique recipe of subatomic particles called neutrons, protons, and electrons. By creating new subatomic particle recipes, we can create new elements that are not found in nature. So it's not that we're creating new subatomic particles, we're just creating new combinations of existing subatomic particles to create new elements. So here's a table of the elements most commonly found in the human body. And you'll notice that over 96% of our body, by weight, is made out of only 4 elements: oxygen, carbon, hydrogen, and nitrogen. And these percentages don't differ very much across living things. So bacteria have a fairly similar percentage. They're mostly made out of those 4 elements as well. And so macronutrients. Macronutrients are going to be things like sugars, fats, proteins, vitamins. Macronutrients are large molecules made up almost entirely of those 4 elements. And then beneath the macronutrients, you find what we call micronutrients. Micronutrients we need in smaller quantities. This is going to be calcium, phosphorus, potassium. Collectively, they make up 3.7% of our bodies by weight. And then beneath that, you have trace elements, which make up less than 0.01% of the human body by weight. And that's your iron, your iodine, your copper. There's many, many trace elements. That we need them in low abundance doesn't mean that they're not important. They could be very important. It's just that usually they're needed in such small quantities that they are easy to come by. But actually not always. One of the challenges of raising captive exotic animals is meeting the unique dietary requirements of a particular species. A zoo might, the macronutrients, we know what they are. We know that everything needs fat, carbs, proteins. But a zoo might struggle to keep a particular animal because zoologists haven't identified all of the trace elements that is required in that particular species' diet. And sometimes humans have a hard time coming by getting enough of certain trace elements. So for example, goiters, this is a Burmese woman with a goiter, they're caused by not having enough iodine. So this happens in places where iodine isn't commonly found in the soil and where they're not buying iodinized salt, right? Because usually there's iodine in the table salt that you buy. So just because something is not needed in large abundance doesn't mean that it's unimportant. One of Carl Sagan's most famous quotes is that we are all made of star stuff. He said this because all atoms, aside from hydrogen, are made in the hot and high pressure center of stars. Now, it's beyond the scope of this course to discuss why, but some elements are made inside stars in a greater abundance than other elements are. So this graph shows the universal abundance of different elements. So you have, oxygen, carbon, hydrogen, helium, et cetera, et cetera. Now, it's no coincidence that the most abundant elements that build living things are also among the most abundant elements in the universe. These are the most available building blocks for life. And this is another way that you could consider us star stuff. What we are made of reflects what the universe is made of. All right, so a compound is a substance that consists of more than one element in fixed ratios to each other. Compounds are more common than pure elements. So an example of a compound would just be table salt. Sodium chloride, that's table salt. It's an ionic compound. And so you can see here, you have sodium here. That's pure sodium, a block of pure sodium. Here's pure chlorine. You mix them together and you get table salt. And it's a compound because table salt is always a 1-to-1 ratio of sodium atoms to chlorine atoms. So the ratio doesn't vary, it's a fixed ratio. And here you're also seeing an example of emergent properties, which we talked about in a previous lecture video. Sodium chloride has properties that are not contained by chlorine or sodium alone. Now, each element consists of only one kind of atom. So an element is a particular kind of atom. So what is an atom? An atom is the smallest unit of matter that still retains the properties of an element. The word atom comes from Greek atomos, which means uncuttable. Atomos means uncuttable. So long before we knew about the real atom, before we knew for sure that atoms exist, in ancient Greece and in ancient India, people imagined philosophically that there must be a smallest indivisible unit of matter. So let's just say you had a cake and you cut that cake in half, and then you take one of those halves and you cut it in half again. And then you take one of those quarters and you cut that in half again, and you cut one of those pieces in half again and again and again and again. Philosophically, they would wonder, could you do, let's say you had the perfect knife. Could you do that forever? Can you make crumbs that are infinitely small? Or do you reach a limit where you get to a unit of matter that is it's not cuttable any further? It's the smallest unit of matter in our universe, sort of like pixels on a computer screen, right? So pixels is like the smallest unit of visual information, right? So is our universe made out of pixels? Is there a smallest unit of matter that cannot be cut any further? And this philosophical smallest unit, this philosophical pixel in our three-dimensional universe, was called an atom. When the atom that we know today was first discovered, we thought it was an indivisible unit of matter, but it turns out we've learned since then that there are even smaller particles. So atoms are built of even smaller units called subatomic particles. So atoms are built out of protons, electrons, and neutrons. However, the name atom does still retain some of its original meaning in that it's the smallest unit of matter that still retains the property of an element. Once you split an oxygen atom, it's no longer oxygen. It's just separated protons, electrons, and neutrons. Okay, so let's take a look at these subatomic particles and how they're arranged. There's going to be three. There's going to be protons, which I will indicate with this shorthand sometimes, and I'm going to draw them just as little red dots. And then we'll have neutrons. Let's make them kind of a drab neutral color. Maybe, well, I'll just make them orange. So neutrons I'll indicate with this shorthand and with a 0 and with that kind of a symbol, and electrons I'll make blue. They're indicated by an E- for their shorthand, and I'll draw them as little blue dots. Okay, so electrons are negatively charged. They have an electromagnetic charge and it is negative. And protons have a positive electromagnetic charge. What does that mean? Well, think about like magnets or batteries. It's just attractive and repulsive forces. So there are these electromagnetic forces, and they come in two styles, positive and negative. The different symbols just mean that they're opposite of each other. Now, one thing to always remember in chemistry is that opposites attract. And let's just write that up here so we don't forget. Opposites attract. Oops. That means that electrons are attracted to protons and vice versa. Another thing is that like charges repel. So like charges repel. That means that electrons repel other electrons and protons repel other protons. Okay, so the way atoms are set up is they have a nucleus. So in the nucleus, you'll find protons, which are these little red ones, these little red particles. And each proton has a +1 charge. And so each proton can attract a single orbiting electron. Each electron has a -1 charge. So when they're together, they cancel each other out. And this little atom that I've drawn here has no net charge. It's neutral because the positive charge in the proton has canceled out the negative charge of the electron. It's the attractive forces between the electron and the proton that keep the electron in orbit around that proton. If the atom has one proton, we can know that this is hydrogen. The number of protons is also the atomic number, which you can find on the periodic table. So the atomic number of hydrogen is 1, okay, because it has one proton in its nucleus. If you add another proton, it's no longer going to be hydrogen. It's going to be something else, like helium. So here's another, this is 2 protons. That's going to be helium, which has an atomic number of 2. Now, the reason the atomic number determines the identity of an element is because it determines how many electrons the element attracts. And the electrons are the most superficial part of the atom, so they're the part of the atom that interacts with the outside world and gives an atom its particular features and characteristics. So helium will always attract 2 electrons because it has 2 protons that orbit around it. And sorry, my circles aren't very good. These two, so these 2 electrons, because it has 2 electrons instead of 1, that's going to determine how it behaves in the world. And so that's what makes it helium. So the number of electrons determine how an atom behaves, and the number of electrons attracted to an atom will be determined by the number of protons in the nucleus. So ultimately, it's the protons in the nucleus that determine the elemental identity of the atom. So atomic number of 2 for helium, atomic number of 1 for hydrogen. And I'll just give you one more example. I'll give you the example of carbon because all biological molecules are carbon-based. So carbon has an atomic number of 6. So say carbon. Atomic number of 6. That means it has 6 protons. And it's going to attract 6 electrons. So 1, 2, 3, 4, 5, 6. And we have 6 electrons. But we'll talk about electron orbitals in a moment. The electron orbitals get full. So you can't fit more than 2 in the inner orbital. So 2 in the inner orbital, full in the outer orbital. We'll talk about that more later. So 6 electrons because there are 6 protons. So where do neutrons come in? So typically, elements have the same number of protons as neutrons in their nucleus. Not always, but typically. Neutrons have a neutral charge. They don't add any negative or positive charges to anything. They're neutral. All they really do is make the atom heavier. That's it. So usually carbon has 6 neutrons because it has 6 protons. There's 6. Usually helium has 2 neutrons because it has 2 protons. Hydrogen's the one example. Typically it doesn't carry any neutrons. It can, but usually it has no neutrons. So we've talked about atomic number. Now let's talk about atomic mass. Atomic mass is sort of like weight, except it's not affected by gravity. You may know that, weight is a measure of how strongly you're being pulled towards the center of the planet, right? The force that pulls you downward. It's a measure of that. So your weight on Jupiter is different than your weight on Earth. Mass is a bit like weight, but it doesn't change from place to place. It's always the same mass. So the atomic mass of carbon, atomic mass is going to be, for this carbon atom, is going to be 12. Because it has 6 protons and 6 neutrons, which makes 12. Why don't we care about the electrons here? Because electrons they have essentially no mass. Electrons are a lot more like light particles, like photons. They carry essentially no mass. So we just tend to ignore them when we're talking about mass. Okay, so the atomic mass for helium, this one here has an atomic mass of 4 because 2 protons plus 2 neutrons equals 4. Protons and neutrons have approximately the same mass. And this particular hydrogen has an atomic mass of 1 because it has 1 proton and no neutrons. If we added a neutron to make a heavier version of hydrogen, which can happen, we would just cross out that 1 and make the atomic mass 2. Right? So the atomic mass is to find it, you just add up the number of protons and neutrons in the nucleus. We can have heavy versions of these elements, not by adding electrons, because those have essentially no mass, and not by adding protons, because while that would make the atom heavier, we would have just created a different element. So if I add a proton to hydrogen, I don't get heavy hydrogen, I get helium, right? Because the protons determine the identity of the element. So that's a whole different element now. If I want to get a heavy version of the same element, I add a neutron, just like I did with hydrogen. So this original version, atomic mass of 1, we would call that 1H. So 1H. That's a heavy that's the normal version of hydrogen. If I make it heavier, I get 2H. That's when I had the atomic number of 2, right? Those are both hydrogen. The heavier version is called a heavy isotope. It's an isotope of hydrogen. So when you change the number of protons, you get a new element. When you change the number of electrons, you get a different electric charge. And when you change the number of neutrons, you just get a heavier element. So what do I mean by a new electric charge? Well, most of the time, hydrogen doesn't have, let's go back to our original version of hydrogen. Most of the time, hydrogen doesn't have a neutron. And it also often doesn't have an electron. That's a sloppy erase, but let's just do that. It often doesn't have an electron. So in that case, what we would have is hydrogen plus 1. So this little particle here, that's hydrogen because it's a proton. It has no neutrons, so it's an atomic mass of 1. And it's actually 1 hydrogen plus. And you could write a plus 1, or you can just write a plus, because there's a proton that's unbalanced by an electron. So before, when I had the orbital there, when the electron was orbiting, you had a positive charge that was canceled out by a negative charge, which made no overall charge, neutral. Now you have a positive charge in the nucleus and no negative charge to cancel it out, so it has a net charge of plus 1. So if you change the number of electrons, you change the electromagnetic charge on the atom. If you change the number of protons, you get a different element. And if you change the number of neutrons, you make the element heavier. All right, so let's look at a heavy isotope of carbon. So if I were to take a heavy isotope of carbon, all I would do is maybe just add another neutron here. So this would be, now we have, instead of an atomic mass of 12, we have an atomic mass of 13. And so we would call that carbon 13, 13C versus 12C. Carbon 12 is the typical version of carbon, but every now and then you get a heavier isotope of carbon called carbon 13. Now, carbon 13 behaves in the same way, generally speaking, as carbon 12, but it's just a little clunkier because it has an extra neutron. Now, we can use heavy isotopes to trace biological processes. For example, you might know that plants turn carbon dioxide from the atmosphere into sugar using photosynthesis. So carbon dioxide, CO2. So carbon dioxide looks a little bit like this, and typically it's made out of carbon 12, the normal version of carbon, but sometimes you get a carbon dioxide molecule that is made out of the heavy isotope of carbon, carbon 13. Now, plants can use carbon dioxide with carbon 13, and make that carbon dioxide into sugars as well, but carbon 13 is more rare, and since it's a little clunkier, plants do tend to take up carbon 12 preferentially. But you can do experiments with carbon 13 to see what plants are doing exactly. So here's a little plant. Let's get this little plant here. So here's a little plant growing, and it takes carbon dioxide out of the air and makes it into sugars, usually using carbon 12. But we can make a dome and trap this plant under it, right? And this dome we can fill with carbon dioxide that uses only, that's built out of only the heavy isotope of carbon. Okay, so now the plant has no choice. It has to use the heavy isotope and incorporate it into the sugars and its flesh to build its body. So what we could do is we can leave it photosynthesizing with the carbon 13 for a while, and then we can dig in the soil to figure out where that carbon 13 went. And what we've learned from these experiments is that plants give a whole lot of their carbon dioxide to their fungal symbionts. So they have roots, but those roots are attached to fungal symbionts that extend through the soil. What the fungi do is they basically are an extension of the root network. They take up nutrients from soil, they mine nutrients from rock, they're really good at getting water even under very dry conditions. So what we've learned from these experiments where we trace carbon 13 is that this plant, some plants will give 75% of their sugars to their fungal symbionts. That just goes to show how valuable the services that the fungi provide are to the plant. We also found that these fungal networks can extend for miles. That greatly extends the reach of the plant roots, because the plant roots are not that long, but these thread-like fungal networks can travel for miles, bringing back nutrients to the plant and trading them for sugars. So the fungi get nutrients and water and trade them with the plant for sugars. Another thing we learned from doing these kinds of experiments is that plants will nurture their young. So there's another plant that might have been a baby. This is an offspring of the plant that we're testing. And somehow it's getting the 13C that we put into the parent plant. So this 13C, which I'm drawing in black, it's traveling through these fungal networks to this baby plant. Plants they can trade carbon with other plants to support each other in a community, and they preferentially give sugars to their own offspring. They nurture their young. These are the kinds of things that we can learn by carbon 13 heavy isotope tracing. You put the heavy isotopes into one organism and see what it does with it. Some isotopes are so heavy that they are entirely unstable, and the subatomic particles in their nucleus, the neutrons and the protons, they break down into smaller subatomic particles that are radioactive and very high energy. And these smaller subatomic particles, they just like pop out, they like radiate out of the nucleus. So those are going to be things like X-rays and gamma rays that are emitted by these unstable heavy isotopes. Radioactive isotopes are used in medical diagnostic tools. So PET images, these are PET images of the brains of a healthy person on the left and an Alzheimer's patient on the right. We use sophisticated imaging instruments to detect radioactive isotopes. So an imaging instrument that uses positron emission topography, or PET, detects the location of radioactive materials that we've injected into the person. So we can see how the brain is using certain materials by giving them radioactive versions of a particular element, right? So we can see how the brain is working, how the heart is working by tracking where these radioactive isotopes are going. So these are really just like tracers that allow us to track their movement within the human body. We also use radioactive isotopes for dating very old materials. When the nucleus of a radioactive isotope decays, protons in the nucleus decay also. And we know that when we change the number of protons in an element, we get a new element. So 14C, for example, that's another heavy isotope of carbon. I talked about 13C, but what about 14C, or carbon 14? This is an isotope of carbon that's so heavy that it tends to break down. It has 6 protons, like all carbon, and 8 neutrons. We know how much 14C is contained in, or carbon 14, we know how much is contained in plant or animal flesh when it's fresh, and how much animals and plants incorporate carbon 14 into their tissues while they're alive. Then after they die, that carbon 14 is unstable, so it begins to decay into other elements that have fewer protons. And that's going to change the ratio between the carbon 14 and the normal carbon 12. So by looking at the ratio between carbon 12, which is the normal form of carbon, and carbon 14, the radioactive version of carbon, we can estimate how old an animal and plant remains are, because those ratios change over time, as you can see in this image. Different radioactive isotopes decay at different rates, so we use different ones to age things differently. For example, radioactive uranium decays into lead over time because the protons break down and then it changes what element you have. So we know the ratio of uranium to lead in fresh magma when magma first emerges from a volcano. And then every year, after the magma has cooled and is sitting on the surface of the Earth, every year more of that uranium degrades radioactively into lead. So that's going to change the ratios of uranium to lead. And we know the rate at which that happens. So we can age rocks by looking at the uranium to lead ratios. This is a better isotope to use to age older things, older fossils, as opposed to carbon 14, which is better for things that are a little bit newer. And just to clarify, carbon always has 6 protons, right? That's what makes it carbon. So if it had a different number of protons, it wouldn't be carbon anymore, it'd be something else. So the atomic number is always 6 for carbon. 6 protons attract 6 electrons, so carbon will always tend towards 6 electrons as well. What is different in these different versions of carbon, these different isotopes of carbon, carbon 12, 13, and 14, is the number of neutrons, right? And now the atomic mass, so the atomic number is the number of protons, that doesn't change. The atomic mass is the number of protons plus the number of neutrons. So when you have more neutrons in an element, you have a heavier isotope and a larger atomic mass. So here, carbon 12 is the typical, most common form of carbon. Carbon 13 is a heavy isotope of carbon, which we can trace through living things and see where it goes. And then carbon 14 is the radioactive version of carbon, which we use for carbon dating. The periodic table is organized by atomic number. So here, if you look at the top here, you have hydrogen at the top, That's atomic number 1 because there's 1 proton. Helium is atomic number 2, then down to the next row, lithium, atomic number 3, 4, 5, 6, 7, 8, 9, 10 is neon, and so on and so forth. So the periodic table is set up to be organized by atomic number, which is the same thing as the number of protons. So hydrogen has 1 proton in its nucleus, helium has 2, lithium has 3, 4, boron is 5, carbon 6, nitrogen 7, 8, 9, 10, so on and so forth throughout the entire periodic table. Now, the atomic mass is listed at the bottom of each square. You see that, like nitrogen, the atomic mass number down here is 14. That's not a nice, clean number like we were talking about before. Like, let's look at carbon. 12.011 is the atomic mass listed for carbon on the periodic table. Why? We've been talking about carbon 12, 13, and 14. Well, on a periodic table, what you'll see for the atomic mass is the average mass of that element and all of its isotopes as they exist in the universe at large. So to get the atomic mass in the periodic table, they take carbon and they look at what the ratios of carbon 12, 13, and 14 are on a universal scale. They estimate the ratios on a universal scale, and then when they take the average. So most carbon is carbon 12, but then there's a few rare carbon 13s and 14s, and so that increases the average atomic mass a little bit, right? That's because of extra neutrons existing in some of the carbons. So, but if you look, hydrogen atomic mass of approximately 1 because most hydrogens just have 1 proton and no neutrons, right? But every now and then you find one with a neutron that increases the average mass. All right, so the last thing we have to discuss is electron orbitals. Firstly, electron orbitals, they don't orbit the nucleus in a flat circle the way we draw them, or like planets around the sun, right? So if I were to draw, the way I drew hydrogen before, I had 1 proton in the nucleus and then 1 electron orbital that it attracts around it. Oops, that's a terrible circle. All right, there's its electron. They don't orbit like that. They orbit in a cloud. So there's a 3-dimensional cloud, and this electron is just zipping all around. These are 3-dimensional orbitals, and the electrons are so fast that they appear to be in all parts of the orbital at once. So these, we call them electron clouds. The orbital forms a cloud around the nucleus. What I'm describing here is a very simplified model of how electrons behave. They have, in reality, all the strange properties of subatomic particles. But we're really going to simplify things. I'm going to give you a simplified model that works for the purposes of biology. But if you want to know more accurate truths about electrons, you'll have to take an inorganic chemistry class, or better yet, a quantum physics class. All right, so here's some functional truths about electrons that do a pretty good job of explaining what we see in biochemistry. All right, so first of all, I told you that each proton in the nucleus attracts 1 electron, but there's some complicating factors here. First of all, even though electrons repel each other, they are drawn somehow to pair up. Unpaired electrons are very unstable. We call them free radicals, and they cause all kinds of chemical turmoil until they manage to pair up with another electron from somewhere else. This means that sometimes an atom will have more or less electrons than protons, and that will create what we call an ion. Ions have a positive or a negative charge. So here, if I were to have this pair up, we would have H minus 1, okay? Because it has 1 proton with its positive charge and 2 electrons with their 2 negative charges. There's an imbalance of 1 negative charge, so it's an overall negative charge on this hydrogen, right? So we have +1 and -2. The result is -1, -1. And then if we have another form of hydrogen with no electrons, that's going to be hydrogen +1, or you can say hydrogen minus or hydrogen plus, because there's a positive charge in the nucleus and no neutralizing negative charge, so that's a hydrogen +1. Now, despite the fact that unpaired electrons are unstable and reactive, because they repel each other, electrons won't pair up unless they have to. So now let's go back to looking at carbon. So carbon has an atomic number of 6. It has 6 protons in its nucleus. It still has those neutrons. I'm not going to talk about them though because it's not really relevant to the electron orbitals here. So carbon has 6 protons. It tends to attract 6 electrons. Now the inner orbital it's full after it takes 2 electrons. Then we have to move out to the next orbital and start filling that. The next electron shell can hold 8 electrons. So these electrons don't have to pair up. They will exist unpaired in this orbital unless they have to. So because they're repelling each other. Another complicating factor is that there are multiple electron shells nested within each other like Russian dolls. This is because each shell can only fit so many electrons inside of it due to limited space and because of the repulsion between electrons. So let's take an element like chlorine. Chlorine has 17 protons. 17 protons in its nucleus. Okay, so now let's look at the kinds of electrons it's going to attract. So the first orbital, it's full once it has 2 electrons. It can only fit 2. It can fit 1 pair, and they must pair up. The next orbital, the next electron shell, it takes 8 electrons before it's full. Now they're going to fill unpaired first, and then we've got to put more until we reach 8. So now we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons. We need 17 to match the protons in the center. So we have 10, 11, 12, 13, 14, 15, 16, 17. We have 1 unpaired here. 1 unpaired, okay? 1 empty slot. Because the third orbital can also take 8 electrons before it's full. So the inner shell, the inner electron shell is full with 2 electrons. The second electron shell is full with 8 electrons, and the third electron shell is full with 8 electrons. So you see how they paired up only when they had to, and we have 1 unpaired electron and 1 empty slot before this outer electron shell is full. There are more shells outside of this third shell, but they aren't really that relevant to biology. Life primarily uses the lighter elements, so we won't be doing any chemistry in this class with elements that are much heavier than chlorine. And it's a good thing too because electron shells and orbitals get really complicated beyond this level. Atoms tend to interact with other atoms in ways that allow them to fill their outer shell. So chlorine is 1 electron away from a full shell. It's going to tend to take electrons from other atoms. If it took an electron from another atom, that's going to create an imbalance between protons and electrons, which means that chlorine is usually an ion with more electrons than protons. So let's look at that. So it's going to get an electron from outside. It tends to do that. Now it has 18 electrons and 17 protons. So we have 17 pluses, but 18 minuses for a total charge of -1. So chlorine, this is the symbol for chlorine, tends to have a -1 charge, so chlorine minus. Now, sometimes the path of least resistance towards a full outer electron shell is to lose electrons instead of gaining electrons. So for example, let's take another case of sodium. Actually, I'll try to fit it onto here. The same slide. So sodium has an atomic number of 11. It has 11 protons in its nucleus, which means it tends to attract 11 electrons to start off. Now remember, you can only put 2 of them in the innermost electron shell, and then we do 2. So 3, 4, 5, 6, 7, 8, 9, 10. Okay, there's 10. It needs 1 more. So that's going to have to move. We've got 8 in the second shell. We need to move out to the third shell. We just put the last one there. All right, so sodium has 1 electron in its outermost electron shell. It needs 7 for that shell to be full. So it could gain 7 electrons, but that's a lot of extra electrons for a pretty small nucleus to attract because there's only 11 protons. it's easier for it to simply lose that last orbital. So instead of gaining 7 electrons, it's probably going to lose 1, leaving the full second shell. So now its outer shell is full, right? But again, we have an imbalance now between protons and electrons. We have 11 protons and only 10 electrons. So 11 plus and 10 minus, that's a net charge of +1. So sodium, so this was chlorine, and sodium tends to have a positive +1 charge most of the time because it tends to lose that outer electron to lose its incomplete shell so that it's left with a full shell, the full shell underneath. So here's a diagram that shows how electrons are arranged in the first 3 electron shells of the elements. So I want to point out a pattern here. The row indicates how many electron shells an element has. So elements in this third row here, they all have electrons existing in their third shell, right? Here in the second row, they only have a second shell. They don't have a third electron shell, right? And in the first row, they have only their first electron shell. And then the columns tell you something about how many electrons you're finding in those shells, right? So we were filling with 1, 2, 3, 4, 5, 6, so on and so forth. Okay, and you have the same organization in the periodic table. So let's look here at how that's organized. You have hydrogen here and helium. They're in the first row, so they have only 1 shell, and they can only take 2 electrons. Here, there's 8 columns in this second row because there is only a second shell, electron shell, which can only take 8 electrons. So these have 1, 2, 3, 4, 5, 6, 7, 8 electrons, and so on and so forth. Now, this pattern is continued into the 4th row and 5th, but we're adding electron shells here, and the 4th electron shell begins to get a bit complicated. Luckily, in this class, we don't have to deal with it. We don't really work with heavier elements. Almost all of the elements that biological organisms are made out of are in these top 3 rows. So we'll just restrict discussion of electron orbitals to elements in these top 3 rows. The next video is going to be about chemical bonds. So we'll take what you just learned about electron orbitals, and we'll apply that to see how different elements interact with each other to create larger molecules.